Hello, welcome to Electrical Circuits part number 10, Series Capacitive Circuit Analysis. Now, whenever we're working with purely capacitive circuits where we have no resistors, no inductors, just the capacitors in there, we have to do a little bit different. We have to flip-flop our formulas. So we'll use the reciprocal formula to find our total capacitance. So C sub t would be equal to 1 divided by, open parenthesis, 1 divided by C sub 1 plus 1 divided by C sub 2 plus 1 divided by C sub 3. And so that would give us 1 divided by, open parenthesis, 1 divided by 10 microfarads plus 1 divided by 30 microfarads plus 1 divided by 15 microfarads. Now remember, I took them from the metric notation to standard decimal to do our formulas. And that comes out giving us a total of 5 microfarads for the circuit. Now we're going to find our capacitive reactance. And so to do that, first off we have to convert from our capacitance to capacitive reactance. And we'll use the formula 1 divided by, open your parenthesis, 2 pi frequency capacitance, close your parenthesis. As you notice up here on the schematic, I'm showing that we have 60 hertz. That's typical for what we get out at the wall here in the United States. We operate on the 60 hertz. And so to plug this in, it'll be 1 divided by, open parenthesis, 2 pi 60 times our 10 microfarads, giving us 265.26 ohms. For our X sub 2, we'd do the same process, but we'd use the 30 microfarads, giving us 88.42 ohms. And remember, our reactance is measured in ohms. It's the opposition. And then for C sub 3, we would use the same process, same formula, but plug it in with 15 microfarads, giving us 176.84 microfarads for X sub C3. And for our total capacitive reactance, we would use that same one, but we'd use our total capacitance. So 1 divided by, open parenthesis, 2 pi times the frequency of 60 times our 5 microfarads, giving us 530.52 ohms total for this circuit. Now to get our current total, we simply go back and use the Ehrenpai Ohm's law. Remember from one of the earlier tutorials, we used Ehrenpai as a memory aid to set up our thumb wheels for Ohm's law. And so if we covered up the I with our thumb, it would tell us that it's voltage divided by the resistance. But because we don't have resistance, we use our ohms, which would be the reactance in this case. So I sub t is equal to V sub t divided by X sub ct. So that gives us 480 divided by 530.52, or leaving us with 905 milliamps. Now, because in a series circuit the current remains constant, we can go ahead and populate the I sub 1, I sub 2, and I sub 3 with that same 905 milliamps. So now we're going to be looking at our voltage drops for the individual capacitors. And so for them, we'll use the Ohm's law again. V sub 1 will be equal to I sub 1 times X sub C1, excuse me. So again, we take our 905 milliamps and put it back in standard decimal notation, times the ohms, our capacitive reactance of the first capacitor, the 265.26, giving us 240 volts. Now, I didn't round the 240 volts off into the two significant digits, because remember, when we're making these calculations for our expected values, that's our baseline, and we have so many variables, temperature, components having a tolerance range, they're man-made, so we have so many variables, a little fluctuation in voltage. So the math that we do for electricity is close counts. It's like in horseshoes. So we'll have the 240 volts drop at the first capacitor. At the second capacitor, we'd use that same basic formula, but specify it for the voltage drop at the second capacitor is going to be equal to the current at the second capacitor times the X sub C at the second capacitor. So our 905 milliamps times 88.42 will give us 80 volts, roughly. And for our third one, we'd do the same process, and it would be 905 milliamps times 176.84, giving us 160 volts. And now we're looking for VARs. You notice we're not using P, we're using VARs. VARs simply stands for voltage ampere reactances on this, and it is sometimes called wattless power, especially if it's a purely capacitive circuit, because your power pulses, you'll have the same power pulses going positive as going negative, and they cancel themselves out, so there's really no real power. And so VAR sub C1 is equal to I sub 1 times V sub 1. So we're using pi. The power formula is still the same one. And I might add that when we're in AC, we always operate off of RMS values for our voltages, our currents, and our power. RMS voltage, root mean square, is simply 70.7% of our AC voltage. That's what we use to make these formulas work, because if we had 100 volts AC or 100 volts DC, it would take 70.7 volts AC to produce the same amount of heat in a resistor that 100 volts DC did. That's why we are able to use these same formulas with a little bit of a variation on there. And so we come out with the 905 milliamps times 240 volts, giving us 217.2 VARs. VAR sub C2 is equal to I sub 2 times V sub 2. So our 905 milliamps times 80 volts will give us 72.4 VARs. And VARs sub C3 is equal to I sub 3 times V sub 3, so that same 905 milliamps times 160 volt drop will give us 144.8 VARs. And our VAR sub T, our total VAR sub CT, would be equal to I sub T times V sub T, so the 905 milliamps times 480 total voltage, giving us 434.4 VARs. Here it all is listed out after we've made the calculations. Again, you would use these calculations that we calculated. You would now go out to the circuit, make your live readings with your meters, and come back, compare them to these. Are we in the ballpark? Doesn't have an issue with that part of the circuit. Is it way over foul ball, over left field? We have an issue there with that part of the circuit. We need to look a little closer. That concludes part 10. Thank you.